So let us start with a very simple example. Let's say a Tic Tac Toe game. All of you are familiar with what a Tic Tac Toe game is. If you are not, I'll just quickly rehash. So we are all uh, going to draw this small line squares, and you have two players and they take turns in putting crosses or zeros, right? So if I put a cross, the player 2 puts a zero or a circle, right? I again put one more cross, the other player puts one more zero, so I put one more cross, right? Let's say the other player puts a zero, then I can put another cross and I win the game, because the rule says that if all the three AIJs are 1 along any row, column or diagonal, that player particularly, that particular player wins the game. Okay, in this case I chose my sign as a cross, so I win the game first, right? Whoever wins the game first wins the game. So I mean, whoever matches with this particular rule. So let's say I want to design a circuit which is going to announce the winner based on the board position. So suppose, assume this entire game to be going on a hardware circuit, and whenever the particular winning situation happens, there should be a circuit that tells you that this is a situation X has won or O has won, right? Zero, whoever is putting the zero or this circular thing has won. Okay, so if you see, the rule is this: if there are three AIJs along, if three AIJs are 1 for any either X or 0 along any row, column or diagonal, the player wins. But unfortunately, this is a natural language expression, right? And this could be ambiguous. Okay, if you want to design a circuit using this thing, it is going to be it could lead to some kind of ambiguity, because this is an English statement. Okay, so what you need to typically do is you need to do some kind of a transformation of this stated statement here into a more mathematically rigorous form, right? So one such transformation could be, I am renumbering these AIJs as 1 or 0. So if it contains a X, I mark it as 1, and otherwise I mark it as 0. Doesn't matter if it is a O, it is 0, even if it is empty, right? Nobody has put any inputs to that particular cell, it is still marked as 0. That is a transformation that I define. It is not has to be whatever I have done, but the designer, right? So the point of this particular slide is to give you an idea of how a designer might think how to approach this problem, right? So from a common man perspective, they will always say that the rows, columns of the diagonal elements has to be all 1 for that particular sign, and you transform the problem into a binary problem, or a problem where you can actually apply rules of Boolean algebra and so on. So you said that, okay, I am going to replace all the AIJs. If there is a 1, if there is a X, I am going to replace that with a 1. So if you look at the top picture that I have drawn, so this is going to be this is going to be replaced by a 1, this is going to be replaced by a 1, 1, 1, and the rest of them are going to be replaced by a 0. Okay, so now the problem is, can we build a hardware circuit that checks the board configuration and declares a winner, right? So maybe you can give an output. For example, it glows a red LED if X wins, and if O wins, it is going to glow a green LED. It's a very simple, typical circuit example that you can come up with, or you can design, right? So this is to give you an idea of this particular system, right? So this system is going to have how many inputs? The system is going to have a total of 9 inputs, A11, A12, A13, dot dot dot, A33. Some of them could be set to either X or O, right? Or it could be untouched, right? So this particular thing can take 3 variables, or like 3 values. It can either be an X, it can be O, right? I put a quotation, or it could be something like let's say U, which is unused, or the user has not given any input, right? So of course we cannot use Boolean algebra with variables that has three possible states, that can take three possible states. We have to somehow reduce the problem into a situation where I can work with only two states, 1 or 0 in this case. That's why I said that if it is, because we are trying to see that who has, like if X has on, I am going to create a different output. If O has on, we are going to create a different output. So if X has on, I am basically transforming this to all the places where X mark is there. I'm going to replace that by 1, and this is going to be replaced by 0, and then we do the rest of the circuit design. So this is to give you a feel into how combinational logic could be used, or even forget about combinational logic, but how digital logic could be used to implement very, very simple computing systems, right? This is like the foundation of creating which are things which are much more complicated than this, right? A real computer is much more complicated than this. Okay, so again, as I mentioned, we are basically building a logic circuit. So if you see on this particular example, we are going to create a logic circuit. It's a logic circuit which is going to have all these 9 inputs from A11 till A33, and there is some amount of computation or logical, I would say logical computation, right? Not really some arithmetic or something is going on here. It's simply some kind of a logical manipulation. By logic we mean there are certain operations in Boolean algebra that we are going to come very soon, like AND, OR, NOT, and so on. So they take all these 9 inputs, perform some kind of a logical computation on those inputs, and it has an output. Maybe this is the output that turns on if X wins. So this is output 1, and this is, let's say, output 2. So this also has to be logical outputs, right? These logical outputs could be connected to something that could be perceived by human beings, or kind of something which is appreciable by human beings. So a logical circuit is only going to give you a logical output. So if in the first case, if X, the person who gives an X mark, wins, I can say that in that case O1 is going to be set to 1 and O2 is going to be set to 0. That is a logical output. This means that X has won. It could be the other case also, where there is O1 and O2, and O1 could be set to 0 and O2 could be set to 1, which basically means that this O has won the game. Okay, so this is basically the logical circuit, and we are going to understand how to design these logical circuits. Okay, so the building build logic structures that, when suitably combined, evolves into a microarchitecture of a computing system. Of course, a computing system doesn't consist of just this Tic Tac Toe game hardware, but it consists of adders, it consists of other, let's say, multiplexer, encoders, decoders, and so on, that we are going to study later, and they are combined in a certain way that makes general purpose computation possible. You can write programs in a computer that can be executed, general purpose program that could be executed, right? Anything that is computational, that is computationally feasible, that program could be executed on your computer. Or and what we try to say here is that we want to build logical structures, or whatever the cell example that I gave, into very, very complicated computing modules. Okay, so those computing modules are meant for general purpose computation, but we cannot build the general purpose computer just like that. It is going to be made up into small pieces, and those small pieces are called the logical structures. Okay, and we are going to concentrate on how to build those logical structures. So this is basically a logical circuit that I am shown here as this purple block. And internally you should remember that this logical circuit consists of transistors that are implemented that are basically implementing logic gates. So logical circuit is going to be implemented using logic gates. If you don't know what is a logic gate, we are going to come to that very soon after we finish the prerequisites on the Boolean algebra. But just to give you an introductory understanding, we are going to deal with binary variables or logical or Boolean variables, and logic gates help you implement the Boolean functionalities at the hardware level. For example, if I have an AND operation, I mention that as A dot B as a Boolean algebra construct, but you can also have the similar thing that is implemented on hardware using a gate circuit, right, which could be an AND gate circuit or an OR gate circuit and so on. So all the Boolean algebra expressions, right, could be implemented in hardware using these gates, and those are implemented using a network of transistors. So that is not something that we are going to look into as a part of this course, but you can know that these gates are actually built using transistors, and when we are building these logical circuits, they are actually built using the logical gates. Okay, so for example, a logical circuit may need 10 AND gates, 20 OR gates, 5 or NOT gates, and so on, right? So keep that information in your mind. And the logical circuit that we are going to develop is going to have a set of inputs and a set of outputs. Both of them are logical inputs and outputs. This is something that you need to definitely understand, right? This is not something which is like typical real values or numbers that we see. Somehow that has to be converted to this binary form, or that is something that could be consumed by this or treated using this Boolean algebra construct. So these inputs has to be logical, the outputs has to be logical, and you can give any meaning to that, right? So for example, every such input could have two states. It's a logical input. It could mean high and low. I mean, it could have two states, high or low. You are free to assign any meaning to what high means or what low means. That is something that I'm repeating, but that is very important. Keep that in your mind. So first, there is a functional specification. So what does this functional specification do? It's a relationship between the input and the output variables. So there are this input, logical input variables and logical output variables. The functional specification tells what is the relationship, how does the input map to the output. That is one thing that has to be specified if you want to design a logical circuit. There is one more thing that is often required. We are going to come into those details later. Is a timing specification. So the delay between the inputs changing and the outputs responding, because often it's not the logical circuit. Whenever it is implemented or even out of requirement, things are not instantaneous. So whenever you put the inputs, it is not that you get an instantaneous change in your output. Okay, so there could be a delay in between the inputs when they are changing and the outputs that they are responding. For example, you can have an input change from 0, let's say, to 1. So this could be logical levels. So if you have the y-axis showing the logical levels, this could mean a logic of 0, this could mean a logic of 1, and similarly in the output you are going to have some kind of a logical change, right? This could be 0, this could be 1. So the mapping of these things, right, what should be the output for a given input is defined by the functional specification. The other thing is that whenever this change happens, let's say this was 0 now and it has changed to 1. So let's say for 0, suppose this is a NOT function or a NOT gate. We are going to know more about it. NOT is just a complement of this particular logical value. If it is 0, it is going to be complemented as 1. If it is 1, it is going to be complemented as 0. But the timing specification is going to tell you the delay in between the inputs changing, the outputs responding. Okay, so let's say this was till a time 1 second, and the next 1 second is going to be, the input is going to be 1. Okay. Similarly, if it is a NOT gate in the logical circuit, so the first 1 second is going to be 1 because it was 0. But you need to remember that, let's say, whenever the input has changed to, so after 1 second, the input has changed to 0. Sorry, the input has changed to 1, right? So let me use a different color. So after 1 second, it has changed to 1, right? So ideally, the output is going to here change to 0 in the next 1 second. But there might be some kind of a delay, that even if your inputs have changed, it reflection in the output is not instantaneous. This is something that you have to also remember, because many of the internal designs, when you try to look at, there are multiple stages of such logical circuits, right? So here you are going to give you one input and one output, and it's a very simple logical circuit. The delay might not be much, right? Although there is a delay, but when you have many such logical circuits cascaded, then it is going to give rise to a significant amount of delay. So unless and until you have this assumption in your mind that each and every such logical circuit has an input and output delay or timing specification, you might end up in some kind of synchronization errors, right? So what you could have is that there is a logical circuit 1, the output goes to another logical circuit, the output goes to another logical circuit, and so on, right? And then you get a final output and you have another input, right? So this is, let's say, input, and this is the output. So what we are trying to say, each one of these logical circuits is going to have an input to output functional specification or a mapping, that for what input what is the output, and then for every such logical circuit, it is going to have some kind of a timing specification or delay, like delta 1, delta 2, and so on, right? So the outputs are going to be expected after some finite amount of time, not instantaneously, right? If you give an input and read the output instantaneously, you might be reading a wrong output. It could be something that has been written by the circuit in the logical output previously. Okay, so this is very important to know when to read the output. Okay, so these are the two things that you should remember about the any logical circuit: functional specification and timing specification. Okay, so combinational logic. So we are going to look into two kinds of logical elements or logical element design. The first one is called combinational logic. We call this as a memoryless design. So the outputs are strictly dependent on the combination of the input values that are being applied to the circuit at that point in time. Okay, so there is no retention. That's the reason we call it memoryless. There is no retention of values within the circuit. So when we, let's say, want to again going back to one of the most common examples in the CPU is adder, right? We want to always add a lot of numbers. You have A and you have B, and you want to give out an output C, which is equal to A plus B. There is nothing that has to be retained, right? That the output has to be kind of calculated strictly dependent on the combination of the input values A and B, right? So you don't have to retain anything in the memory, or anything from the history is not going to take any role in that, or even the next set of computations once you do try out, let's say, A prime plus B prime, where A prime and B prime are the new set of inputs, that does not depend on the previous computation A and B, right? So just reiterating, suppose you have a circuit which finds out the sum, right? It's like an adder circuit of A and B, you get an output of C, right? So the output C is strictly dependent on the combination of input values A and B, number one. Number two is that next time you want to update these values and you want to compute the sum for different set of inputs A prime and B prime, and output being C prime. This has nothing to do with the previous set of computations that we have done. Okay, so these we are going to clarify that more, and this set of circuits, right, or this set of digital logic implementation are typically called combinational logic. Okay, in contrast to combinational logic, we are going to also learn about sequential logic. Initially, we are going to start with combinational logical building blocks. Next, we are going to look into sequential logic, which stores the history, right? The main difference is that the first one was memoryless, whereas this has memory. So, what you do next is often dependent on what happened in the circuit in the previous time step. Okay, so it can store data values. Of course, it could be used for designing memory systems or storing data, right? The storage units could be made using these principles of sequential logic. So the outputs are determined by the previous or historical values as well as the current values of the inputs. So if you look at the combinational logical elements, it is going to be strictly dependent on the current set of input values, whereas in case of sequential logic, it is not only the current values but also the outputs that was or the previous state of the system, right, where the previous output will be important. Okay, so if you think of this A prime B prime example, so C prime here, suppose it was a combinational circuit, not only just depends on A prime and B prime, but it also depends on C, which was previously computed. Okay, this is just a hypothetical example I am trying to give to contrast with combinational logic example that we had earlier. But this is more important. The outputs are determined by the previous, not only the current, previous plus the current values. Okay, current inputs. So each one of them are pretty, there's a lot to study in each one of them individually. So we are going to take up combinational logic first after we are done with the Boolean algebra primer. And once we develop a good number of use cases or building blocks using combinational logic, we are going to move on to sequential logic that has things related to timing of a circuit, or when you study about the organization of a computer, there is a vital component of how these instructions are executed one after the other. So there is a timing or a concept of a timer or a clock that is going to come, right? So we are going to cover them when we start studying about the sequential logic. So what is functional specification? The functional specification of the outputs in terms of inputs, that is what the functional specification is. And what do you mean by a function? Many of you know that, okay, function means this has to be a onto mapping. So this has to be the first criteria is uniqueness. So this is a mapping of the unique set of input values to the output values. Okay, so the mapping has to be unique. So you cannot have one input value is going to give rise to multiple output values. Okay, that is not unique. Okay, however, it might be the case that you have two different input values that can give rise to the same output value. That is a different thing, right? But for every input value, there has to be unique mapping to a output value. Okay, there is this unambiguity. That is what I just now said. The same input values produce the same output value every time. So it is not only it has to be unique, but also it cannot be ambiguous. That sometimes it creates one output, sometimes it creates another output. That is not acceptable. So the same input values, whatever has been mentioned in the functional specification, has to be repeated, right? It has to be reproducible or repeatable. Okay, so every time the same input value is going to create the same output value, and there is no memory dependency here. So there is no history of input values that are tracked, or even the outputs that are not tracked somewhere, right? So the function purely depends on a set of input values and how it maps to a set of output values. There is nothing in between, no memory or nothing from the previous historical computations that has gone in the circuit. Okay, so now back to the tic tac toe game that we have just now introduced. We were interested in kind of designing a circuit for this. We are not going to design the entire circuit right now because that requires us to go into much more details about how to design combinational circuits, but we can always scratch the surface and see how things look like. Okay, so in this case, as you see that there were, I will redraw the circuit that we had this logical circuit that we need to build. We had these 9 inputs starting from A11 to A33, and we can come up with an output scheme that we feel like. Either it could be having 2 outputs or 1 output, or however we want to convey the information to the rest of the world, who is the winner, right? So that is how we need to come up with the design. So we have to create a functional specification, right, of this particular circuit, and this is what is done by a truth table. Okay, so the truth table does what? It basically has the or implements the functional specification, the relationship between the input and the output variables. So if you look at the top, there are these 9 input variables, A11 to A33, and W, this could be kind of treated as the output, and our output is that if X wins, we want to output a 1, otherwise we don't want to output anything. It basically, the output is the default output, which is 0. Okay, so we want to output only 1 if that person wins, right? So for example, if you see the first set of the row, you see that A11 is set to 1, so that contained an X. A12 contained this is 1, this is 1. A13 contains 1, A22 contains 1. The rest of them are 0. I don't care. Okay, so this is definitely so A12 contains a 1, right? Sorry, this contains a 1. So this is definitely a situation when we can always strike this off. So this is a situation when the player X or whoever, whatever mark we use, right, for representing 1, that person wins. So this is a winning condition, right? So if this is true, like if this is true, right, all this is the functional specification. This is a set of inputs, and this is a output. This is one row right here in the truth table. Okay, so the truth table is going to be used to list down the entire set of functional specifications. Okay, the relationship between the input variables and the output variables. You can have one more situation where I can erase the previous markings. Okay, and look at the next thing, the next row. Let's say here, in case of this particular row, let us try to see what this input is. A11 is 1, then we have 0, then we have 1, then we have 0, 0, 1, so 0, 0, 1, then we have 0, 1, 0, so 0, 1, 0. So if the logical circuit that we are designing is asked that tell me whether this is a winning situation for this particular person who is putting 1, we would definitely say no, right? Because we do not see that this is going to be resulting in a winning move by this particular person. Okay, so neither we can complete this nor we can complete this, right? Nor we can complete this, or nothing in the diagonal exists, right? So this is not going to be a win by that particular player, right? So this is going to be resulting as in a 0. Okay, so as you can see, what is going to be the size of the table. So as you can see that this is pretty exhaustive job, right? So the functional specification is going to be encoded in the truth table, and the number of such entries, the number of rows in the truth table can be pretty large, right? So this size grows exponentially with the number of variables, right? Because every variable or every input here is a boolean, is going to be a boolean value which can hold two possible states. So a11 for example can be either 0 or 1, a12 can be either 0 or 1, and a33 can be either 0 or 1, right? And in between all such variables can be either 0 or 1. So the number of the unique possibilities or the number of unique inputs that can be there in this table is 2 multiplied by 2 multiplied by 2 dot 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 multiplied by 2, right? Because it could be 0 or 1 and the rest it doesn't matter. So for every unique combination of this particular entire set of inputs, you can have two of them, one with a11 with a 0 or a11 as a 1, right? So you are going to end up in 2 to the power n inputs where 2 to the power n rows where n is the number of inputs. Okay, so that is the reason we say that the size actually grows exponentially with the number of variables or inputs, you can say, inputs to the logical circuit. So often it is a very complicated task to deal with a truth table that has so many rows and so much of like huge size, right? Because at the end of the day we want to design a circuit that consists of, in this particular case, 2 to the power 9, which is 512 such rows, and every row is associated with an output. And think about the number of different things in this huge table. So you have 9 inputs and 1 output, so there are 10 columns and there are 512 rows. So we are dealing with 5120 such bits, right? So 9 plus 1 columns, right, and 512 such rows, right? So this is really large number of values that we are trying to deal with. So one of the things that we are going to see as a part of our exploration of how to make this, how to come up with designing such circuits and so on. So we are going to see that can we make this concise or easier to communicate or express, because if you want to hand over this functional specification even to a colleague who is going to take up the design, this is not an efficient way to do this, right? And we cannot use a natural language because this could be ambiguous, right? We have to somehow come up with a representation in the language of mathematics that is not going to be ambiguous. Okay, so the target is, can we make this concise or easier to express or communicate, right? So that you can come up with manipulations of this design. Suppose you want to combine this design with another design, you cannot keep on writing this huge truth table of 512 entries, right? So we need to know certain ways, some standard ways of representing this functional specification, not just exhaustively jotting them down in form of a truth table, but using some kind of Boolean algebra functions. Okay.